Okay, hey, so we're talking about projectile motion a little bit today. It says a ball is thrown off a balcony. Plus, a pretty classic projectile motion question horizontally at 18 meters per second. Determine the position of the ball at 1, 2, 3, and 4 seconds. Show these positions on a scale diagram. And what's the mathematical name of the resulting curve? So if you kind of, study projectile motion, most physics textbooks will have a picture of one of these things where something falls off. The rate at which an object falls horizontally is the same as the rate at which an object falls. Did I say horizontally? I meant vertically, as another object that falls, but it also has a sort of forward motion to it when it starts. Notice the red ball moved this much in that last period of time, while the white ball moved that same amount in the downward position, but it also had some forward motion, right? And if you look at the grid lines here, notice that the white ball and is moving forward, and notice the distance between all of these lines, these grid lines, is constant, implying that it is a constant forward velocity. But the distance between all of these grid lines here that move in the up-down direction, it appears to be increasing, implying that the ball, while moving forward constantly, is moving downward with an acceleration. Okay? And we all know that acceleration is 9.8 meters per second squared. Okay? And oftentimes that's going to be labeled g with a vector, and that's the acceleration due to gravity on planet Earth at the around the sea level there. So how do we determine the position of the ball? Well, we want to basically take these in two separate scenarios. Here's the x and the y, and I'm going to do it for 1 second. Okay? Well, since in the x direction it's moving horizontally at a constant velocity, that means that I know that velocity equals distance over time. Okay? And I know that the initial velocity x was 18. So if I stick an 18 in here, and there's a box. I stick an 18 for velocity in 1 second here. So that means 18 times 1, algebra, is going to tell me that the distance traveled is going to be 18. So when t equals 1 second, the distance traveled in the x direction is 18. When t equals 2 seconds, then I'm going to use the same formula. It's just going to be 18 meters per second times 2 seconds. And that's going to be my distance traveled for 2 seconds, which is, 18 times 2, which is 40, 30, 36. And then for 3 seconds, I think you're going to catch the issue here. So I'm moving forward for 3 seconds at 18 meters per second. And I end up getting a 54. Okay, meters, and so forth. And then for 4 seconds as well. It looks like they want us to do 4 seconds. So for 4 seconds, it's 4 times 18. This is my horizontal position every second. So, you know what I mean? Here's my graph. I went ahead and made it, or pulled it out of somewhere. And what do we have? We have a 72 here. So now if I do the same thing for the y component, noting that my initial velocity y is 0 meters per second because it started off horizontally. So in the beginning, its vertical y velocity is 0. Well, knowing from my kinematic equations, I know that I've got a formula that says Oops, I wrote that wrong. I got a formula that says d, or delta d, or change in position, is equal to the initial velocity times the time plus the 1/2 acceleration times the time squared. Okay? All these are vectors. Vector here, here, and here. Now, this works in the y direction. So if I put a y here and there for my vectors, and my acceleration vector is also in the y, which I can call my gravitation. Instead of using g, you'll sometimes see me use acceleration y. Okay? But since my initial velocity y is 0, this whole term just becomes 0 right here. Chink, chink, 0. So I can figure out my displacement in the y direction by just canceling out this term, because it's always initial velocity of 0, and then inserting various times, 1, 2, 3, 4, into this section of the formula. So for my 1 second situation, my dy is a 1/2 negative 9.8 times 1, or 4.9 meters per second. Oh, sorry, no, these are meters. It's meters. When the displacement is, or when 2 seconds have elapsed, so I'm just taking 2, okay, then it's 1/2 negative 9.8 times 2 squared. And I'm going to end up getting about a 20. Okay. And when 3 seconds have elapsed, I end up getting a 3 here. And you can kind of see the pattern here. This is 44 meters. And after 4 seconds have elapsed, I can see my pattern of negative 9.8, and I get 78. Oh, these are all negative, sorry. So effectively, if you notice my graph here, look what ends up happening is at 1 second, it's moved forward 18 and down 4.9. So forward 18 and down 4.9. After 2 seconds has elapsed, it's moved forward 36 and down 20, so 36 and 20. And then after 3 seconds and so forth, I can see that forward's 54 and down 44, so forward 54 and down 44 and so forth. Here's my 4th second. And there it is. Okay, this was just a basic kind of question where we started off with a horizontal velocity, no vertical velocity, and we're just sort of trying to map out the shape of this sort of pattern. And as you can see, what's the mathematical name of this resulting curve? It's a parabola. Hence the name parabolic motion. Okay, which is sometimes the name of this chapter in some textbooks, right? Or it's kind of interchanged, projectile motion, parabolic motion, and so forth. Okay, let's start taking a look at some more complicated examples. Here we've got a helicopter traveling horizontally at 82 meters. While it's 82 meters above the ground. Pilot prepares to release a relief package intended to land on the ground 96 meters ahead. Air resistance is negligible. The pilot does not throw the package, but just lets it drop. What is the initial velocity of the package relative to the ground? Okay, so this question here and the previous question are similar in that effectively, if I take this picture here and bring it down for us, pretend like you've got a helicopter flying here. This is 82 meters above the ground, and there's a place where he wants it to land right here, and that happens to be 96 meters in advance. So let's pretend like this is 96 and this is 82. 82, I'll write it over there so you can see it a little bit better. And effectively what's happening is, if the helicopter's going too slow through here, helicopter moving too slow, then the package will drop here. Okay? If the helicopter's moving fast when he drops this package, moving too fast, the package will drop over here. It'll kind of be going too quickly, right? Question is what is the precise velocity that the helicopter needs in order to drop this package perfectly 96 meters in front of it when it knows it has to fall 82 meters vertically? That's kind of the idea here. So what we're going to try and do is gather up some y and x components here. So I know in my y direction, my initial velocity y is 0 because I'm dropping this. I'm not throwing it. Actually, in fact, it says it right there. The pilot does not throw the package up or down. It lets it drop. So when you see lets it drop or drops or falls, something like that, this is an indication that the person who wrote the question is wanting you to make the assumption that the initial y velocity is 0, meaning it has no vertical speed at the very beginning of the question. But then as soon as you let it drop, it starts to gain downward vertical speed. So, but we'll calculate all that as things unfold. I also know that gravity is going to be, the acceleration due to gravity is going to be a negative 9.8 meters per second squared. Okay, I'll make that into a negative. Let's see, what else are we able to assume here? I'll make this a big screen so we can have more space. We also know that my vertical drop is going to want to be negative 82 meters. That's what I know. Basically, I'm saying that this is y negative, the y negative direction. And I'm going to make this the x positive direction. Okay? And now the question is I've got other variables. I could find how long it takes for the thing to fall that far. And then I could back calculate based on that, knowing how long it takes for it to fall, and then knowing that it needs to travel 96 meters forward during that length of time, I could then back calculate my initial horizontal velocity. So I think I'll do it like that, okay? So knowing that my kinematic equations are as such, delta dy is 1/2. No, sorry, I skipped a section. This is correct what I did, but I want to initial velocity y times delta t plus 1/2 acceleration y times delta t squared. So again, remembering that my initial velocity y is 0, this term goes away, okay? And so placing my variables in here, I got negative 82 equals 1/2 times negative 9.8 times delta t squared. Solving for delta t, I got another question down here. I got to move him. I'm going to move him real quick. Solving for delta t, I'm going to divide this stuff over and then square root it. So therefore, my time is going to be plus or minus the square root of a negative 82 divided by half of a negative 9.8, which is equal to 4.1 seconds. So effectively what we've discovered here is it takes about 4 seconds for this thing to fall to the ground. Okay, now knowing that it takes 4 seconds to fall to the ground, I know that Vx is equal to the change in velocity, change in displacement, change in position, x, over the change in time. Meaning that the horizontal velocity that it has is equal to the rate of change of its horizontal position divided by the amount of time that it's been falling. Okay, well, we know it's been falling for 4.1 seconds. Okay, and note that, so I'm just plug this stuff in here. I know that it needs to fall 96 meters. Sorry, it needs to move forward 96 meters. So I'll plug that in there. And I know that it needs to fall for 4.1 seconds. And boom, I'm going to get my x velocity, which is 96 meters per 4.1 seconds. And this makes sense because this is a meters per second calculation. So it's 23 meters per second. And effectively what we're saying here is if this thing is moving forward at 23 meters per second, when it drops the package, then 4 seconds later, the package will hit the ground, and during those 4 seconds, it will have moved forward 96 meters, effectively hitting this target that we were wanting to hit. Okay? So in both of these cases, this one and the previous one, we were dealing with something moving forward horizontally. Here we were given the initial horizontal velocity and asked to figure out where is the thing sometime into the future. Whereas in this question, we were given some location that we would like to be in sometime in the future, and we were asked to calculate the initial conditions that needed to be in place in order to effectively hit that target. Okay? Now, let's check out this one. A medieval prince, here he is trapped in a castle, and he wraps a message around a rock and throws it from the top of the castle wall with an initial velocity of 12 meters per second at 42 degrees above the horizon. The rock lands just on the far side of the castle's moat. Here's a moat right here. Right? A moat is like a liquid defense barrier around the castle. Okay? And at the, at a level of 9.5 meters below the initial level. Okay? Okay, so it looks like from the location from which he releases the rock is 9.5 meters down. And it lands just right on the other side. Okay? Just on the far side there. Determine the rock's time of flight. Determine the width of the moat and the velocity of the rock at which when it hits the ground here. Okay, so we've got some work to do. All right, so again, I'm going to set up some conditions. I'm going to say that my delta dy is negative 9.2 meters, okay? Or sorry, 9.5. That should be a 5 here, okay? Let me get rid of that 2 and make it into a 5. Okay, And we also know that my acceleration due to gravity, I could write a g, or I could write ay, acceleration in the y direction. I'll write that this time so we can kind of get used to both notations. That's negative 9.8 meters per second. This is a medieval prince, so medieval Earth had an acceleration that's equal to today's acceleration. And what else is given? Oh, shoot. You know what? This time it's been thrown 12 meters per second upward. So it wasn't thrown horizontally, okay? So what that means is if I sort of take my initial velocity vector here and put a 12 right there, and then a 42 degrees here, I actually have two components, an initial velocity y and an initial velocity x, okay? And maybe I'll zoom in on this for our viewers here. All right. And the question is, well, how do I get these two values? Okay. Thinking about this as a right triangle. Why is it a right triangle? Well, because y and x are defined as being perpendicular to each other. So they're always going to be perpendicular to each other, right? If they're not perpendicular to each other, then they're not y and x. So they're going to be, okay? My hypotenuse is 12. I've got an angle of 42 here. So this is basically an initial velocity, right? So basically what I can do here, to find my initial velocity y, I'm going to set up the following. The sine of 42 is the opposite side, initial velocity y, which I don't know currently, divided by the hypotenuse, or 12. And so therefore I've discovered that my initial y velocity is 12 sine 42. And by the same reasoning, I know that my x velocity is cosine of 42 Vix over 12. Because 42, the adjacent side, is initial velocity x, okay? And now if I multiply my 12 over, I'm going to get 12 cosine 42 equals initial velocity x, okay? This is now my initial vertical velocity, and this is my initial horizontal velocity, okay? And if I type those into the, calculator, I'm going to get 8.9 and 8 for this one. So my initial velocity x is 8.9 meters per second, and my initial velocity y is 8 meters per second, okay? Now this is a common technique. It's going to be called getting vector components. It's a really important thing for physics students to be able to do, all right? You'll notice after doing this many, many times that essentially always the initial velocity y is equal to 12 sine of launch angle, and initial velocity x is 12 cosine launch angle, okay? So don't worry about that too much. I mean, it's pretty, it happens a lot, okay? So let's go over to here, and now let's go back to our drawing board here, and we're going to say that my initial velocity y is 8 meters per second, okay? Now that I've got I can find my flight time. Again, this is a similar situation where I need to find my flight time, but I also need my impact velocity, okay? So I'm going to try and find my final velocity y as well. Okay, I need both of these. And through a little bit of experience and having done this in the past a few times, I know that it's easier to find my final velocity y first and then my time rather than my time and then my final velocity. And the reasoning is, what I'm about to do, I'm going to erase. If I choose this formula, delta dy, let me make this a bit smaller here. If I choose this formula, delta dy is equal to initial velocity y times time plus 1/2 acceleration in the y direction times time squared. And notice in this case, I have an 8 here rather than a 0, an 8. And I'm still trying to solve for t. And then here I've got half of gravity, which half of gravity is 4.9. Okay, so I get a negative 4.9 t squared. And then over here, I'm going to get a negative 9.5. Okay, if you look closely at this, this is a quadratic. So, and I've got a t and I've got a t squared unknown. If I have a t and a t squared unknown, what I actually end up having is two solutions. And I'm going to have to take it, I'm going to plug this into the quadratic formula, which is going to be a bit of an annoyance, right? Because I can then figure out that t is equal to negative b. Well, b is 8, so negative 8 plus or minus the square root of 8 squared minus 4 times a. A is negative 4.9. And c is 9.5, 9.5. It's not negative because I have to pass it over to the other side here. Because remember, in order to use the quadratic formula, the whole formula needs to be set equal to 0. So passing this guy over to here is going to be what I would want to do. Then I'm going to divide this by 2a. Oh, knowing that a is again, what's a? Negative 4.9. Now I have to go ahead and type all of this junk into my calculator. And it's a bit, oh gosh, a bit of a bear. And I discover that t is equal to 2.4 seconds. Okay? And so that's what that's going to be. And I'm going to get 2.4 seconds. But this is, I don't know, cumbersome. This is annoying. Let's call it that. Annoying. I can't even spell annoying, but that's what it is. Okay? So I don't do it that way. What I suggest students to do is find your final velocity y first, because look at this fancy formula. Final velocity y is equal to the square root of the initial velocity y squared plus 2 times the acceleration due to the gravity times the vertical displacement. Okay? And look at this fancy little formula. Don't forget there's a plus/minus here. So, knowing that that's my formula, I'm going to go ahead and plug this stuff in. So I get 8 squared minus 2 times the acceleration, negative 4.9, times the displacement in the y direction, negative 9.5. Okay. And bam, when I go ahead and plug all this stuff in, when I plug all that stuff in, I end up getting, what do I get? Oh, no, sorry, I wrote 4.9. This is supposed to be 9.8 right here. 9.8. Negative 9.8, because that's the acceleration due to the gravity. Remember, I'm pulling directly off of this list. I'm not using these numbers up here, these green numbers. These green numbers are annoying. Okay? But I wanted to show you two techniques here. Anyway, this is what I'm doing. And I calculate this and I get two solutions. I get a positive or a negative 16 meters per second. Now, question is, which is right? What's happening here? Let's look at our picture. At the end, is the thing moving upwards or downwards at 16 meters per second? It's clearly moving downwards. And so I'm going to choose the negative 16 meters per second here. So I'm going to get negative 16 meters per second. That's my final velocity y. Okay. Now you might say, well, that's all great fun, but don't forget, Mr. Knapp, you said that the green stuff is annoying, and we never did that. So what that means is we still actually have to find our time. So in order to find the flight time, I know that the acceleration due to gravity, or I know that the flight time is equal to the initial velocity y minus the initial velocity y. I meant final here, guys. This is final velocity y. Velocity final y minus the initial velocity y over the acceleration due to gravity, okay, which is the acceleration in the y direction. That should be a y, okay, in the y direction. And if I plug this stuff in, what's my final velocity y? Well, I didn't have it before, but now I do. I know it's negative 16 meters per second. And I know that my initial velocity y was 8 meters per second. And my acceleration due to gravity is a negative 9.8 meters per second. And if you plug all that junk into a formula, guess what you're going to get? 2.4. Okay? 2.4 seconds. Pretty awesome. So I'm going to erase this green 2.4 and write that one. Okay. Now again, why did I do that? Because this calculation here, look at how easy this is. This is 16 minus, basically 16 plus 8 divided by 9.8, and I got 2.4. Whereas up here, I had to plug everything in, pass something over, don't forget to mess up my negative signs, take my A's, B's, and C's, plug them into the quadratic formula, and then calculate two answers, one of which is going to be negative and throw it out, and then the other one is going to be positive, and that's going to be the correct answer. So I'm just saying you can do it like this green way, but this light purplish way is a little bit more, user-friendly. Anyway, 2.4 is my flight time. Okay? And we found that here. So we can also now find the velocity at impact. Okay? Well, the velocity at impact is essentially, it hits the ground like this. All right? Well, I don't know. I'll draw a vector that's a little bit more. Boom, it hits the ground. Let's pretend like this is the ground right here. Okay, and it hits the ground with a velocity. And I want to make sure that this, so when it's hitting the ground, it's coming down like this. Boom. You don't want to draw your vector like here. You want to keep it down over here, right? And now we know that when it hits the ground, it had a negative 16 meters per second in the y direction. And don't forget that it also had some horizontal velocity, which was 8.9 meters per second. Where's that guy coming from? Remember, way up here. Let me unzoom. Remember way up here when I was talking about my initial x velocity? It was 8.9 meters per second. Well, that's the velocity that it initially had horizontally. But we know that in the horizontal direction, that the velocity never changes. It's only the vertical velocity of a projectile motion that changes. The horizontal velocity never changes. So you can assume that it maintains 8.9 meters per second forward during the entire 2.4 seconds that it's in the air. Okay? Meaning that its final velocity here has two components, a horizontal component, which we'll label Vx, and a vertical component, which we'll label Vfy, okay? Now notice the orientation of these two components. They are at right angles, and the final velocity is the hypotenuse of this triangle. So I can now say, well, the final velocity is just the Pythagorean theorem using these horizontal and vertical components, okay? So I'm going to take the x component of 8.9, square it, and then I'm going to take the y component of negative 16 and square it, okay? Note that if I square a negative 16, it's going to be positive. So I generally just elect to not write the negative, knowing that it's going to be positive anyway. And now I go ahead and I calculate this. Putting these back together in a sort of Pythagorean theorem thingy, I'm going to get a final velocity of 18 meters per second. Okay, and this is the final velocity. And I'm going to put magnitude symbols around this because I don't have this is just the magnitude. I don't have the angle yet. If I would like to find the angle, it's here. Okay, and knowing that that is the angle, well, a pretty quick and easy SOHCAHTOA lets me know that if I can use the tangent inverse to find the angle, because I have the opposite OA and the adjacent OA, SOHCAHTOA, opposite and adjacent. So I know that the tangent inverse of the opposite, negative 16, over the adjacent, 8.9, is going to be my angle, okay? And that angle turns out to be 60 degrees negative, okay? So I know that my final velocity is a negative 60 degrees, effectively explaining that, yeah, that's a negative 60 because it's going down, it's below horizon, okay? And so since I did put the vector or the angle here, I can now actually erase these two guys because, well, I went ahead and put the thing there, right? So this is the answer to part C right here, velocity at impact. But I still have to figure out the width of the moat. Uh-oh, I didn't do that yet. So that would be this distance here. Well, that's pretty easy. I'll do that over here. How do I know, how am I going to find that? This is just like the helicopter question where I know the thing was in the air for 2.4 seconds and it had a constant horizontal velocity of 8.9. So knowing that the velocity in the x direction is equal to the change in position in the x direction, or the horizontal direction, divided by the length of time that it's flying through the air, I end up getting, what do I want to solve for? I want to know how far it went or how big the moat is. So I want to know this variable. It's horizontal change in position, horizontal displacement, or its range, sometimes called the range. So if I plug these two numbers in, this is 8.9, this is 2.4, so I'm going to get 8.9 times 2.4, and this is delta dx, and this is meters per second, and this is seconds. Bang, I end up getting the length of the moat, which is 22 meters. All right, so that was a pretty exciting question there. Lots of stuff going on. We were able to determine that a quadratic formula can be used, but it tends to be annoying. And so there's other ways of doing that by finding first the final velocity, then the time. With the time, you can then figure out the horizontal displacement or the range. And then with the final velocity, And the x component of the velocity, which is over here, you can find the final velocity here, okay, the total final velocity. I said that wrong. To find the final velocity, you need the x component and the y component. In fact, this is the formula for it. Final velocity is equal to the square root of the x velocity plus the initial final y velocity squared. Note that here I've got a final velocity and here I don't. Why would it? Why the reason why there's no reason to put an f here, because the initial velocity and the final velocity in the x direction are always the same. The velocities in the x direction never change, so there's no reason to put an f for an I here. I put an I over here, but in the end, I don't need it. In fact, I'll get rid of it. But I do need to put the i's and the f's in the y direction because, remember, as things fall, their y component, their vertical velocity is constantly changing, whereas their horizontal velocity stays constantly the same, I guess. Doesn't change. Anyway, so that's what we're looking at. That's the idea, projectile motion. All right. A couple of sample questions there was.